Hi, my name is Jorge Jacinto, and today I will be presenting on this study which developed a method for quantifying the concentrations of various different cannabinoids in cannabis plants using high throughput liquid chromatography with tandem mass spectrometry. So, as you probably know, THC has become a widely used substance in recent years, both for medical and recreational purposes. And as more and more states legalize cannabis, it has become increasingly important to regulate the quality of products making it to the shelves of licensed dispensaries. So, as you can see, a lot of states have already legalized cannabis for both recreational and medical use. And a lot of other states are on track to do so. So, as you can imagine, it's going to be very important to regulate the quality. So this has given rise to businesses whose primary purpose is to provide third-party regulatory testing for companies that make cannabis products. It is important that the testing is performed by a third party in order to avoid any conflicts of interest that may lead to a falsification of data. So I actually worked at one of these laboratories. Here's the logo for it. It was called Canalysis. And from my experience in working in this laboratory, we took these codes of ethics very seriously, and we wanted to make sure that consumers were obtaining safe cannabis products. And because the main goal of such laboratories is to ensure safety, most of the tests involve checking for the presence of toxic chemicals such as heavy metals, such as lead, mycotoxins, pesticides. We also tested for microbes such as E. coli and mold. We also did a terpenes analysis test. We did a residual solvents analysis. So a lot of these, as I mentioned, are for safety. But in my opinion, the most unique test we did was the cannabinoids test, because this one we wanted to quantify the concentrations of all the different cannabinoids present in the plant material with high precision, rather than just giving a binary pass or fail based on whether or not the compound was present or not, like we did for all the other tests, like for pesticides. So for the cannabinoid test, we really wanted to be precise, and again, this is important because we want to make sure that people are obtaining the right doses. You don't want people purchasing a product that has a higher dose of THC than what they actually want. So so what is the separation problem that we're going to be discussing? So here I have put images of the structures of three of the cannabinoids of interest were looked at in the study. So here we have THC, in the middle we have CBD, and over here on the right we have CBN. So as you can see, all of these compounds are fairly nonpolar in nature, and then some like THC and CBN are extremely similar. So they're going to have extremely similar polarities, um, which emphasizes the importance of choosing appropriate conditions which are going to allow for good separation of compounds with very similar polarities. So this study in particular actually looked at 6 different cannabinoids. So here we have THC, CBD, CBN. They also looked at THCA, THCV, and CBG. THCA is actually the acidic version of THCA. It basically just has this carboxylic acid group substituted in right here, and CBD also it has that normally. So THC and CBD are biosynthesized in this acidic form, but this form isn't stable, and it gets decarboxylated when exposed to heat or light, which gives rise to the structures that you see here. So that also emphasizes the importance for choosing a good method, because a lot of the compounds in their biosynthesized form are not stable. So we're going to want to still be able to analyze those and quantify the concentrations. So why is HPLC with tandem mass spec the most appropriate chromatography technique for the separation? So historically, 2 separation methods, namely gas chromatography and HPLC, as mentioned, have been mainly used for most research dealing with the analysis of cannabinoids. Some works have actually pointed out that one-dimensional gas chromatography doesn't offer enough resolution to separate such complex mixtures as these. And then some studies have actually successfully used 2-dimensional gas chromatography to establish chemical profiles of cannabis. However, using gas chromatography does pose some problems since it requires a derivatization step in order to detect and quantify the thermally acidic cannabinoids. So the ones that I mentioned earlier with the carboxylic acid group that comes off. So these may become decarboxylated upon injection. So that's going to make the prep a little bit more delicate and the test and the method more delicate. So HPLC, on the other hand, can analyze these acidic compounds without the need for this extra derivatization step. And basically what that is, a derivatization step is just like an extra step to add some sort of chemical modification in order to still be able to identify that compound, even if it becomes decarboxylated. So uh, the fact that HPLC doesn't need this is a major advantage because it allows for a more complete cannabinoid profile of the cannabis products. So here I just kind of put this diagram of HPLC. I'm sure most of you know how this works, but I just kind of want to include that in here to just kind of show the method that we're using. So in terms of instrumentation itself, the instruments that they used were HPLC mass spec instruments with triple quadruple analyzers. However, since these do not allow for structural identification of non-target compounds, they went ahead and used time of flight analyzers as well in order to extract the fingerprints of the less abundant cannabinoids. The reason for this is that time of flight analyzers provide accurate mass identification for both the precursor and the product ions. So this allows us to differentiate between compounds that have the same overall mass, but different elemental composition. So I included over here on the right, kind of what that time of flight analyzer looks like. And then over here on the left, you have just the Agilent instrument that they were using, the HPLC instrument. So yeah, this is another method that they use, this time of flight. So it kind of complemented the HPLC mass spec, tandem mass spec method that they were using. So overall, it used the HPLC with tandem mass spec to quantify 6 major cannabinoids, and then it used the time of flight analyzer in order to identify the additional less abundant cannabinoids. So now let's talk about some of the results. So briefly, before I actually get into what this figure is here, I do want to mention that one of the results that they found was with the solvents that they tried. So one of the main issues that need to be addressed in the separation problem was the choice of solvent, right? And so they ended up trying 6 different solvent mixtures. They tried water or methanol with ammonium acetate, water or methanol with formic acid, and then water or methanol with both formic acid and ammonium acetate. And they ended up finding that the best option was the methanol or water with formic acid, particularly at 0.1% formic acid, since this provided the best conditions for separation of the target analytes. So they actually decided this by taking into account which solvent provided the best peak shape and the best sensitivity. They also used a central composite design in order to optimize the effect of mass spec acquisition parameters. And they used peak areas that were obtained for a standard mixture of CBD, THC, and CBN as the design responses. And then they did a multiple linear regression in order to build the response surface. So that's kind of what we're looking at here. But basically what that revealed is that the main factors affecting peak area were the heated vaporizer temperature and the nebulizer pressure. So yeah, those are the 2 main factors that affected peak area. So here on the x-axis, what we have is the vaporizer temperature, and then on the x-axis, you have nebulizer pressure. And that's basically what this is showing here. It's a response surface of vaporizer temperature and nebulizer pressure. And as we can see, there's a local maximum, which is this red area here, which is kind of defined by this low to medium heated vaporizer temperatures. And then it kind of fits in this medium nebulizer pressure range. So this particular surface is actually for CBD in particular, but they found the same exact pattern for all the other analytes with a similar shape of the surface and maximum. So to check for the trueness of the developed method, they actually did different aliquots of methanol, and they spiked them at 2 different concentration levels within the calibration curve range. So they did 3 replicates in the low concentration range, and then another 3 spike samples in the high concentration range. And then the trueness was found to be acceptable for all the cannabinoids. As you can see here in this table, we have pretty good values, both for the low concentrations and the high concentrations. So I just kind of wanted to show that because it shows the quality of this method that they were able to develop. So they actually went ahead and compared it to other methods of extraction, and I thought it would be nice to show this as well. And this was in order to assess the accuracy of the developed method. So this is just a representation of THC and THCA concentrations of different cannabis plants extracted by supercritical fluid chromatography and then analyzed by HPLC with the corresponding standard deviations. So they looked at 10 varieties of cannabis, and these were analyzed in triplicate by the supercritical fluid chromatography, and the results were compared with this HPLC mass spec method that they developed in this study. Unfortunately, due to the lower sensitivity of the supercritical fluid chromatography method, the concentration of the major cannabinoids were the only ones that were determined. And the concentrations of these that were obtained by both methods seem to be statistically comparable. So if you look at the red and blue bars, very similar. Also, if you look at the yellow and the green bars, also very similar. So yeah, I just thought it'd be nice to show this comparison to another method, the SFC. So the last thing I kind of want to go over is this scan chromatogram. So this is a scan chromatogram of the cannabis sample extract where THC and THCA were not analyzed. And basically the main takeaway from this figure is that it shows which compounds were found using the scan mode, which was used in order to obtain the mass spectra of the extracts with complete information and precision. So as we can see, they were able to detect an additional 7 cannabinoids besides the ones that they already knew. And these were actually identified based on the scan mode data and then by referencing the literature. So these 7 identified cannabinoids were then had their identities verified using the HPLC time of flight analyzer that I had talked about earlier. And again, that's because it provides good measurements for both the precursor and the fragment ions. And then over here on the bottom, we have this table that lists the names of the identified cannabinoids over here on the right, along with their masses. So I just thought it'd be a good idea to show this because it shows the high level of precision of this method. They were able to quantify the masses of these previously unidentified cannabinoids that were present in the sample, besides the ones that they knew about. And in the previous slides, I showed the trueness and the precision in comparison to other methods. So yeah, I think this was a very interesting study, which showed a way in which we can tackle the separation problem of separating cannabinoids and using HPLC to do it. So thank you for listening.